So welcome to the second lecture on the basics of algebra, and today we are going to speak about rings and fields, which are going to build on what we did the last time on groups. Okay, so first we need to start by a few definitions to define what a ring is, and then work with the basic concept. So a ring is going to be a set. Is going to be a set A together with two laws, addition and multiplication. So these are laws of composition as we had in the case of groups. And we are going to ask for some properties. So the first property we are going to ask for a ring. So we say that this is a ring if and only if by definition. So first property we ask is that A together with addition should be a commutative group. Commutative, or remember the other word, abelian group. Okay. The second property we need is going to speak about multiplication. So we want multiplication to be associative. Okay, and we also wanted to have a neutral element. And to emphasize that it is neutral for multiplication, we are going to call it the unit element. And very often we will write this unit element as 1. And the neutral element for addition, we will write it as 0. Okay. And the final property we need is linking the two operations together, and it is called distributivity. And it is something you are really familiar with integer. And this property states that for all elements in the ring x, y, and z, we need to have x plus y times z to be equal to xz plus yz. And we also need the other side, so z times x plus y should be equal to zx plus zy. Good. And now, given a ring, we will say that it is commutative. So A is commutative. So clearly it cannot be a statement about addition because addition is always commutative. So it's going to be commutative if and only if, by definition, multiplication is commutative. And this is something we will encounter very frequently. Okay. So what else do we need? So we are going to look at this ring, and in the ring we are going to look at some elements. So we are going to look at the set I'm going to call U, which is a set of elements in X that have inverses. So what is an inverse? It's an element Y such that X times Y equal 1. So we want the existence of y, and we also want the existence of y prime such that y prime x equal 1. Well, when the ring is commutative, only one of the two is needed. Okay? And now this thing is going to be called the group of units of the ring. So not the difference between units with an S, which is not the same thing that the unit element without an S, and the group of units, well, as its name says, it is going to form a group for multiplication. Okay, so let's take a simple case that you know about. So example, Z together with the standard addition and standard multiplication forms a ring, and in Z, the group of units is a very simple set that only contains -1 and 1. And you can check that this set with 2 elements is indeed a group for multiplication. Good. So that's a basic definition of rings. And now we are going to move. To fields. So let's take some more room. And so what is going to happen is that when you look at this set of unit U, there is a very special case. Is when U is basically everything. So when U is a ring without 0, and we want it to be non-empty, so we ask that 1 is distinct from 0, because clearly 1 is always invertible. So this is a special case we want, and which is a special case where all elements are invertible in the ring. And when we have a ring with that property, we say that A is a division ring. And in fact, if A is a division ring, and A is commutative, we say that A is a field. A is a field. Okay, so because of the definition, a field is always going to be commutative. Every element which is non-zero is going to be invertible in the field. And furthermore, 1 is going to be different from 0. So any field will have at least 2 elements. Good. So now we can turn to the follow the same kind of map that we did for groups, and turn to subrings and subfields. Okay, let me take the pen. Good. So now we have, let's take a ring A and take a subset B of A. So we say that B is a subring of A if and only if, by definition, we have the following property. So first, we look at the group structure. So B should be an additive subgroup. Second property, we want 1 to belong to B. And third property, we want B to be closed by multiplication. So remember, this means that if you take any pairs of elements of B, then their product is also going to be in B. And now, a subfield is simply going to be a subring of a field, which is also a field. So let's take an example of why you can have a subring of a field that is not a field. It's a very simple example. If you know the rational numbers, you might know that they form a field because, well, we have this ring structure and everything non-zero is invertible in the rational number. And Z is, of course, a subset of Q. And it is a ring. And in fact, it is even a subring of Q, but it's not a subfield because Z is not a field. Nice. So let's move. As we did for group, we are going to consider now maps between rings. So let's assume that we have 2 rings. Maybe I call them A and B. So a homomorphism is going to be a map F from a ring A to a ring B, satisfying a few properties. So the properties we want the image of the 0 of A, let's write it this time, should be the 0 of B. The image of the 1 of A should be the 1 of B. And we would like addition to go through, so we want the image of the sum to be the sum of the images for any pairs of elements, and the image of a product to be the product of the images. And because of all this property, you can show that the image of the inverse of an element is the inverse of the image, and so on. And like we did with group, we are going to define the kernel of a morphism. So the kernel of F is simply going to be its kernel as an additive morphism of groups. So it's going to be the set of elements in A such that f of x equals 0. And again, we can define the notion of isomorphism by saying that f is an isomorphism if there exists a morphism G from B to A such that f composed with G is identity on B. Yes, and in the other direction, it should be identity on A. Okay, and then we say that f is an isomorphism. Good. And so, for example, we could yeah. So, for example, we can look at some kind of trivial isomorphism. So we have a trivial morphism for example, if we have Q and Z, there is a morphism called the embedding map, which simply sends an element of Z to the same element, but viewing it in Q. Okay, so, and in that case, the kernel is clearly reduced to 0, so this isomorphism, this morphism, sorry, is going to be injective. Good. So now in a ring, on top of subrings, there is something really interesting that occurs. Is something that is called ideals. So let me take my, okay, good. So we are going to say that a set I, a subset of A, is an ideal if and only if, by definition, the following property occurs. So the first property we want is we want I to be an additive subgroup of A together with addition. Okay? So that's the first property involving addition. And the second property we want is we want the set I times A to be included in A. So there is one thing, in the non-commutative case, there are two kinds of ideals. There are left ideals and right ideals. But I don't want to go into that, so I'm for the moment considering that the ring A is commutative. And okay, so this is an ideal. Let's give an example. So for the case of Z, any n, you take any number which is in Z, and you look at n times Z, and this is going to be an ideal. And you might see that according to the definition, there is one special ideal, which is the ideal 0, which is just 0 times Z. And then you have other ideal. You have Z itself, which is 1 times Z. You have 2Z, which is an ideal, or 101 times Z, or anything, any number times Z. This forms an ideal in Z. Okay, why? Because let's check the So the first property is clear because we saw it already. And let's check the second property. Well, if you take an element, so let's say I to be n times z, and you take I in the ideal, you take any lambda in z, we know that I is n times something. So I time lambda is n time mu time lambda. So it's also a multiple of n, so it also belongs to E. So we have the properties that the product of this ideal by the full ring is included in the ideal. Okay, and in fact, this is equality. This is equality here, since 1 belongs to the ring, and multiplication by 1 is just identity. Nice. So now let's take a few examples of ideals. So we already saw an example of you take an element and you multiply the full ring in the case of Z. And in fact, this is a general construction. So for any ring A, and for all element A in A, I equal A times A is an ideal. Okay, and ideal which have these structures are called principal. So this is a principal ideal because it's obtained by multiplying an element by the full ring. And in general, when you have a ring, you can have ideals that are not principal. But there are special cases and there are special rings in which all ideals are principal, and these are called principal rings. Principal rings. All ideals are principal. And an example of such a ring is Z. And we can leave this proof as an exercise. Nice. So another example of ideal. So I'm going to show you other construction of ideals. So another example of ideal is if you have a ring homomorphism F from A to B, then the kernel of F is an ideal in A. And more generally, if I is an ideal in B, then F minus 1 of I, so I'm going to define this as the set of all elements of A such that f of x belongs to I. So this set is an ideal in A. And the first statement about the kernel is just a special case by noting that the kernel of F is the inverse image of the ideal 0. Nice. So now, given ideals, let's say I and j, we can define operations on these ideals. So we can define I plus j, which is the sum of all elements from I and j. So it's a set of sums with x in I and y in j. Okay, and this is an ideal. In A. So for example, if we take 4z, which is an ideal in Z, and we add it to 6z, which is an ideal in Z, we get another ideal in Z, and this ideal is going to be 2z. And it turns out that this is a very general thing, and the number that occurs here is going to be the greatest common divisor of the two numbers of 4 and 6 here, in that case. So that's the sum of ideals. The second thing we can do, given two ideals, is we can consider their intersection. Okay, and the intersection, so the set of elements which belongs to both ideals, is also going to be an ideal. And for example, if we take 4z intersection 6z, what we get is 12z. And the number we get here for the case of ideals in the integers, the number we get here is the lowest common multiple of the two numbers. Okay. And finally, there is another construction which is slightly more complicated, which is the product of ideals. And it is slightly more complicated because if we just take products of elements, we are not going to get an ideal necessarily. So in fact, the product is defined as the set of all sums x1, y1 plus x2, y2, etc., all finite sums of this form, where all the x are in I and all the y's are in J. So the product of two ideals is a slightly more complicated construction. Good. So now that we have ideals, so remember, an ideal is in particular a subgroup. So if we take A together with plus and multiply, which is a ring, and we take I, an ideal in A, we know that in particular I is a subgroup of A. So we remember from last time we were able to build a quotient group A over I. And it turns out that this construction is also compatible with multiplication, and we are going to be able to define a quotient ring where addition is going to be modulo I and multiplication is going to be modulo I. So I didn't define what modulo I meant in general for an ideal, so let's do it now. So we are given two elements x and y in A. We say that they are equal modulo the ideal. So we say that x is congruent to y modulo an ideal I, if and only if x minus y belongs to the ideal. So remember when we did that with numbers, saying that x was congruent to y modulo 5 now becomes the same thing as x congruent to y modulo 5z, which means that x minus y is a multiple of 5, which was exactly the definition we had before. Okay, so we can build this quotient ring for whenever we have an ideal. Okay, so in particular, remember last time we looked at numbers at arithmetic modulo n. So we looked at z over nz as a group, and we saw that this was indeed a group, a special case of the quotient group. And in fact, it is now a special case of the quotient ring. So z over nz is going to be a ring whenever n is, it should be a non-zero ideal. It shouldn't be the trivial ideal, otherwise you can't do the division. Okay. And this ring gives some interesting examples. So let's take the ring, let's say Z over 21Z. So this is going to be a ring, but in that ring we are going to have some bizarre equations that occur. So in this ring, if we take 3 times 7, we find, well, you all know that this is 21. So this is going to be congruent to 0 in modulo n. So it means that we have a ring where you have two elements which are not 0, but their product is going to be 0. Okay, and this is especially bad because for this kind of ring, there is no way to turn them into fields. So you are going to have to deal with bad cases when you look at these rings. And in that case, when you have Z over NZ, if you just consider multiplication, it's really interesting to only work with numbers which do not have this bad property. Okay, so only work with numbers which are units, as we defined before, and so we want to look only at the units. Look only at units. So elements which are invertible, and if they are invertible, they can't have this bad property of dividing 0. And we will note this Z over NZ star. And it turns out that this will be the set of all number x mod n, such that the GCD of x and n is 1. So in the special case, it means that any multiple of 3 should be removed, and any multiple of 7 should also be removed. Good. So now we are going to look at the definition of, we are going to work with field now a little bit. And let's say that K is a field. So remember, it is going to be a ring, it is going to be commutative, and every non-zero element is going to be invertible. This is a field. Okay. So when you have a field, we say that K is a prime field if and only if K has no strict subfield. So of course, when you have a field, it's always a subfield of itself, but this is not interesting. But we want to know whether a field has subfield. So let's give example of field with subfield. So normally you know the field of complex number. So you know that the reals are a subfield in the complex number, and you know that the rational numbers are a subfield in the reals. Okay? So typically, this is not going to be a prime field. This is not going to be a prime field. Okay, so let's now try to find out what the prime field can be. And we will see that there are not so many options. So there is one special option, which is going to be Q, in fact. And there are other options which are going to be finite prime fields. Okay, so let's take K a general field. How can we find the prime field that is in there? So we are just going to take the element 1 in K. And well, we can always take 1 plus 1 plus 1 n times. So this is a very easy construction. And this gives a map from Z to K. We just send the number n to n times 1 in K. So n times 1 being 1 plus 1 plus 1 n times. And this map is going to be a ring homomorphism. So what we do now, we look at the kernel of this morphism, and we know that it's an ideal. So two things may happen. So either this ideal is trivial, so the kernel of f can be just 0, in which case we have an embedding of z in k. And since k is a field, every element of z is going to be invertible. So if 3 will have an image, but then 1/3 will have an image. So we will have, in fact, an embedding of the rationals in k, and we can extend f to a map that sends all the rational into k, and this map is going to be injective. So the prime field in k, so we will see q as a subfield in k. So the prime field in k is going to be the rationals. Okay. The other case is that the kernel is not the trivial ideal. So in that case, the kernel must be an ideal of the form n times z. Okay. So now basically 3 things may happen. Okay, so the first thing that you can consider could happen is n equal 1. But this would mean that the image of 1, which is by definition just the 1 in k, would be 0. And this is not possible. Because we said that in any field, 0 should be different from 1. So this case is not possible. So n must be bigger than 1. And now let's look at n, and let's look at its factorization into prime. So we have two cases. Either n is prime or it's not. So if it's not prime, you can write n as a product of two numbers, let's say a times b. But now, if you look at the product of a times b, you find that the image of a times b is 0 on one side, but it is also the image of a times the image of b, and none of the two can be 0 because they don't belong to the ideal. And this is a problem because if you have divisor of zeros, they can't be invertible. So this is not possible either. So it means that now n is prime. So the kernel of f is in fact a prime number times z. Okay, so now given any field k, we have two cases. Either the prime field in k is form of all the rational numbers, and in that case we say that the field has characteristic 0, or the kernel of f is p times f, in which case the prime field is going to be z over pz, which is a finite field, which is just arithmetic modulo p, and in that case it turns out to be a field. And we will say that the field k has characteristic p. Good. And these finite fields are something we are going to use a lot in cryptography, and you will see them frequently. So let's look. Let's have a quick look at, so we are going to note them for prime p. We are going to note fp as the finite field z over pz. Okay, and this, in this field, so you are going to have a few very interesting properties in this field. So every element except 0 is going to be invertible because it's a field. Fp star together with multiplication is, like for arithmetic modulo n, going to be a multiplicative group. And this group is going to be cyclic. So it means that it will have a generator. There will exist an element G in Fp star, such that for every H in Fp star, H is going to be a power of G. Okay, and this exponent is going to be determined modulo the order of G. So since the group is cyclic, the order of G is going to be the order of this group. So the order of G is going to be equal to the order of Fp star. And remember that the order of the group is just its cardinality, so it's P minus 1, because we remove 0 from the set. Good. So this is a very important group that you need to remember. So now we turn to something which is a very useful tool, both from a mathematical and a computational point of view. We will not do the computational version today. We will just look at the mathematical theory, but it's something extremely important, and it's called the Chinese remainder theorem, and people often just call it the CRT, just using the initials. So in order to be as clear as possible, I'm going to give you the general version with rings and ideals, and at the same time, I will give you the special case with Z, or I will detail the special case with Z, because this is also a very important context where we use it. So let's A be a ring. And assume that we have ideals I1 up to IT, ideals in A. And further, we assume that for every pair of ideals, of distinct ideal, their sum is the full ring. Okay, in that case, we say that the ideals are co-prime or relatively prime. Okay, so these are the hypotheses of the theorem. And now let's give me numbers x1, well, elements, sorry, x1 up to xt in A. Then there exists x in A such that x is congruent to xi modulo ideal number I for all i's. Okay. So let's translate the statement of the theorem to integers. So we are just taking z. Then we take ideal in G, but remember, ideal in G are in Z, sorry, are just given by our principles, so they are given by a generator. So it's the same thing as giving number, let's say n1, nt in A, saying that the sum of ideal is equal to the full ring, just means that for all I and G distinct, the GCD of Ni and Ng is going to be 1. These statements are the same. So now if you give me x1, xt in Z, there is going to exist x in Z such that x is going to be congruent to xi modulo each of the Ni. Okay? And this is the classical form of of the Chinese remainder theorem. Nice. So first, I'm going to start with a special case with just two ideals. So we have, let's say, I and G, which are two ideals, and you give me, and we know that I plus G is equal to A. So what does this mean for two ideals? Well, it's exactly the same thing as saying that there exist two elements, I and G, in I times J, such that I plus G is simply 1. Okay. So now you give me, let's say, X and Y, and you want me to give you Z, such that Z is congruent to X mod I. You want Z such that Z is congruent to X mod Y, and Z is congruent to Y mod G. And in fact, you can check that if I let Z to just be X times G plus Y times I, then this works. So why does it work? Because you can check that I belongs to the set I, so to the ideal I, so it's congruent to 0 modulo the ideal. And because of the relation here, I is congruent to 1 modulo the ideal J. And for J, it's just the reverse. It's congruent to 1 modulo I and to 0 modulo J. So if you take this, it's clearly going to be congruent to X modulo I and to Y modulo G. Okay. So in fact, the special case is easy, and we can move to the more general case to show that we can do something similar in the general case. Okay, so let me clear the screen, and so you should remember the case for 2 because we are going to need it in the proof of the case for more. Okay, so now you give me just plenty of ideals, I1 up to IT, and pairwise you know that I plus IG is simply the full ring. Okay. So what do I know first? I know that I know the following. I know in particular that I1 plus I for I different from 1 is just A. So it means that there exist two elements, xi and yi, whose sum, sorry, there exists xi I need to clear that up. So there exists xi in I1 and yi in yi, such that xi plus yi is just equal to 1. Okay, so we know that. So now let's consider the product of the xi plus yi from I equal 1 to t. Equal 2 to t. So this is of course 1 on one side. But now if you expand the product, you can see that there is one term, which is just y2 times y3 times yt, and all the other terms have some x, plus all terms with x, all the other terms have some x in it. Okay. But since x is in I1 in all cases, every element here belongs to the first ideal. So their sum, because ideal are additive subgroup, the sum of all these terms belong to I1. So let's call it big X. So now we know that big X plus y2, y3 up to yt is equal to 1. And this is in the ideal I1, and this is in the product ideal. This is in the product ideal I2, IT. So this means that the sum of I1 on the product ideal is 1. Good. So now, according to what we did previously, it means that there exists an element y1 such that y1 is congruent to 1 modulo I1, and y1 is congruent to 0 modulo the product I2, IT. But if it is 0 modulo the product, it's also 0 modulo any of the I for I bigger than 1. Okay, so we did that for the first ideal. So we have an element that is now 1 modulo the first ideal and 0 modulo all the others. But by following exactly the same construction, just reversing the roles of the ideal, we can get an element which is 1 modulo ideal number 2 and 0 everywhere else, or the same for any of the ideal for any of the ideals. So now, once we have done that, it means that we have y1, y2, yt, and if you look at them modulo I1, I2, it, you find 1 on the diagonal and 0 everywhere else. So now, if you just give me values you want to see, let's say alpha 1, alpha 2, alpha t, then clearly the element alpha 1 times y1 plus alpha 2 times y2 plus alpha t times yt is congruent to alpha I modulo II for all I. Okay, and this gives the result we wanted for the. This gives the result we wanted. Okay. Good. So now let's go back to the case of integers and see what happens. So for the case of integer, let's assume that we have m1 up to mt, which are pairwise coprime. So the GCD of mi mg is 1 in every case. Okay, and so we have seen we see that what we have done before works, so that there are going to exist numbers which are going to be congruent to 1 modulo 1 of the ideal, modulo 1 of the number, and to 0 modulo all the other of the number, and we can lift exactly in the same way to satisfy all the constraints. But this is essential, because if the GCD is not 1, then the equation might be incompatible. Okay. And now what we are going to do is we are going to look at the following thing. We are going to look at the map that takes an element in Z and send it to Z over M1Z times Z over M2Z times z over mtz. And as a corollary of the Chinese remainder theorem, we are going to understand the behavior of this map. So, okay. So the first thing is that because of the Chinese remainder theorem, this map is going to be surjective. Indeed, if you specify any numbers in the target, you can lift them as number you can view them as number in Z, and you just want some number which is going to be congruent to the first modulo M1, to the second modulo M2, etc. So this is exactly equivalent. The surjectivity of the map is exactly equivalent to the CRT. So now we want to know what is the kernel of this map. So clearly, M1, M2, MT, the product of all numbers, is in the kernel. Okay, so it means that the kernel contains M1, MT times Z. Okay. And now, so because the kernel contains M1 MT times Z, if we just have a number given modulo M1 MT, the way it's going to be mapped is independent of the exact number, but is only going to depend on the class modulo M1 MT times Z. And now, just by a counting argument, you know the cardinality of the image, which is just M1 times M2 times MT. The kernel cannot be bigger than this, otherwise there wouldn't be enough image to be surjective. Okay, so it means that in fact F induces a bijection from Z1 over M1 MT Z to Z over M1 Z product Z over MT Z. Okay, and this bijection is a ring homomorphism. So in fact, it's going to be an isomorphism of ring. Good. So this is just a reformulation of the Chinese remainder theorem or corollary of it, but it's kind of very useful. And now we are going to use it to prove some other theorem, which is often known as Euler-Tauschent or Euler-Phi function. So what is that? So it is just take n, any integer, any natural integer, and consider z over nz. So what we want to do now is count the number of elements which are invertible in z over nz. So remember, if n is prime, then it's every one except 0 is invertible, but otherwise any multiple of a prime factor of n is going to cause some problem. And we would like to count exactly what's going to happen. So what you do is you take n and you look at its prime decomposition. So it's going to be p1 to the power e1 times p2 to the power e2 times pt to the power et. Okay, and thanks to what we just did with the Chinese remainder theorem, you know that there is going to be a ring isomorphism between z over nz and z over P1 to the E1z times z over P2 to the E2z times z over pt to the et times z. Because any powers of distinct primes are of course co-primes, so their GCD is 1. Okay, so this is an isomorphism here. It's an isomorphism of ring. Okay, and now this isomorphism of rings is doing something very nice. It is inducing an isomorphism of groups between the multiplicative group here and all the multiplicative groups there. Because you can check that if something is invertible on the right, it must be invertible everywhere on the left. And if it's invertible on the left, it must be invertible everywhere on the right. And if it's invertible everywhere on the right, it's also going to be invertible on the left, because you can inverse all the value, lift by the Chinese remainder theorem, and you obtain a global inverse. So it's clear that this induces an isomorphism between these multiplicative group structure. Okay, and what we want to know is the size of the group on the left. Okay, and by the way, I need to introduce a notation for this size. So the size of the group on the left is just denoted phi of n. And it is just going to be the product of the size on the right, phi of p1 to the e1, phi of pt to the et. Okay. So for prime numbers, you already know the size of the multiplicative group. You know that it's for a prime number p, it is just p minus 1. Okay, so not happens with p squared? So any number which is not a multiple of not coprime with p squared has to be a multiple of p. And modulo p squares, they are just p multiple of p. And in general, every element in P1 to the E1, which is a multiple of P1, you can only have P1 to the E1 minus 1 of them. And you have exactly P1 to the E1 minus 1 of them. Okay, you just have to choose which multiple of P1 you are taking, and the multiple of P1 is determined modulo P1 to the power E1 minus 1. So this means that these numbers are just P1 to the E1 minus P1 to the E1 minus 1, Pt to the Et minus Pt to the Et minus 1. And this is usually rewritten as P1 minus 1, P1 to the E1 minus 1 times P2 minus 1, P2 to the E2 minus 1, all the way to Pt minus 1 to the times Pt to the Et minus 1. Okay. So, and this uses the Chinese remainder theorem just to count the number of elements which are invertible modulo n in a very easy way. Okay, and of course, if the exponents are all 1, then the number of invertible elements is just the product of the prime number minus 1. And we will see that this is used a lot when doing crypto. And in particular, this is going to imply something very interesting that I want to write down. And by combining this Euler phi function together with the fact that we saw last time about the group of the order of an element dividing the order of the group, and this is going to imply something very interesting. So it means that in Z over NZ, if x is invertible, then x to the phi of n is going to be 1. Because remember, the order of x is the smallest exponent, which makes this power into 1. And since the order of the element divides the order of the group, which is Zn star we saw before, it must divide the cardinality, which means that x to the power the cardinality must be 1. And this is very important. And if you apply it to primes, it means that in Z to the power Pz star, x to the p minus 1 is equal to 1 mod p. Okay. This is called Fermat's little theorem. And if you don't like the fact that this only holds for the element in Zp star and would like something that would hold over Zp, you can do something nice. You can say that over Zp, x to the p minus x, well, x to the p is always congruent to x mod p, which is a nicer form of this, and which is very often encountered under the name of the Frobenius map in the finite field Fp. And this concludes our lecture for today. So hopefully I will have you again next time for the third lecture. So bye-bye.